Okay, so this problem reads, a 5 times 10 to the 5th kilogram subway train is brought to stop from a speed of 0.5 meters per second in 0.4 meters by a large spring bumper at the end of its track. What is the force constant K of the spring? All right, so there's a couple ways you can do this problem. We're going to do it through energy. So if we do it through energy, let's make sure we understand what is happening in this problem. So imagine that you have this train and it hits this giant bumper that then compresses, bringing the train to a stop. So whenever we think about energy problems, we want to remind ourselves that the total energy at one point in time, we'll call that initial, has to equal the total energy at another point in time, we'll call final. And so we want to identify what those 2 points in times are. What is the initial, what begins, and when are we going to look at it later? So for this case, we're going to say that that initial time is right when the train hits the bumper. And the final time, we're going to say, is when the spring is compressed. All right, so when it's compressed, and this happens when the train has a velocity equal to 0, when it's come to a stop, okay? And that's going to be important. Now, when we think of energy, we want to remind ourselves the types of energy we possibly could have. We have, in mechanical energy, we have energy of motion, kinetic energy, and that's if something is moving. And then we have potential energy. We're dealing with a spring, so we have the possibility of spring potential energy. And then we also have the possibility of gravitational potential energy. Now, with gravitational potential energy, we want to remember that that requires really a change in height in our problem. We could say that this object has gravitational potential energy, but since there's no change in height, the initial gravitational potential energy and the final gravitational potential energy are going to be the same. So we can actually ignore those in our problem, because if we set this at our height equal to 0, then there's no gravitational potential energy. So we're left with kinetic and potential energy due to that spring that's involved. And so the total initial is going to be the initial kinetic energy plus the initial spring potential energy. And that has to equal our total final, which is the final kinetic plus the final spring. All right, so then we look at our initial and final conditions and see if we can reduce this even more. When the train hits that bumper, right at that hit point, it is moving. So we have kinetic energy, but the spring has yet to be compressed. So there's no potential energy of the spring. At the end of the motion, in our final situation, the train comes to a stop. And so there's no kinetic energy, but the spring is compressed. And so there must be potential energy of the spring. All right. So we are left with 1/2 mv initial squared, which is our kinetic energy, is going to equal our potential energy, which is 1/2 k delta x squared, our potential energy of the spring. All right, and now it's a matter of using the information that the problem provides us. So 1/2, the mass of the train is 5 times 10 to the 5th kilograms, and it starts with an initial velocity of 0.5 meters per second, and we want to square that in our kinetic energy. And that's going to equal 1/2. K is what we're interested, that spring constant, that says the spring compresses by 0.40 meters. And so we have that compression of the spring squared. Great. So now we just solve for our K value. And when we solve for our K value, so our halves, actually, they kind of go away. This equals a specific amount we know, and all we have to do is solve for K. We find that K is equal to 7.81 times 10 to the 5th Newton per meter. So, real straightforward problem. Once we use energy, we could have solved this with kinematics and force analysis. but we can solve it really quick with conservation of energy. Recognizing what type of energy exists, identifying those 2 time points, one is initial, one is final, then making it convenient to solve, being clever and using our strategies about when we want to set those initial and finals to make our energies 0 in some cases and easier to solve. Good job.